Hi everyone. Yeah, my name is Roger. It is spelt wrong, but that's the way I spell it. Don't know why. Ridiculous 16-year-old boy decided to change his name, lived with it for the rest of his life. So there you go. So we're going to be talking about logs and how they can ideally provide kind of consistency, scalability, and discoverability through what I consider to be simplicity. It's a really, really simple process, but it's one that most people kind of totally ignore. So first of all, what we're going to look at, so a quick agenda. Going to go through what a log is. So I suspect most people in here have an idea of what a log is right now. Going to try and play with that idea. Then we look at what makes logs interesting, or what I think makes logs interesting. Obviously, this is all opinion. And then the third piece is what can logs facilitate? So again, given that I think that they're interesting, why do I think they're interesting? What value do they have? And where can they be actually applied? So what logs aren't? Let's start with that. So for the context of this particular talk, we're not talking about the stuff that this chap, this particularly handsome chap, let's be honest, with this plaid top. We're not interested in logs as parts of trees. More interestingly, perhaps, is we're not talking about logs as in what software developers use to identify and debug systems. So I suspect everybody in the room at some point in the last 24 hours, let's be honest, has looked at some logs that's coming out of, their Apache or their Nginx system, or something that their SQL server is spewing out, explaining something that nobody really understands. We're not talking about that either. Those kind of logs, those human-readable logs, are really interesting, and there's a huge body of work that you can look at as to how they can be advantageous too. But for the context of this talk, we're not talking about. So what are we talking about? So a definition. I've made this look a little bit like a dictionary. No real reason why. So what we're talking about is append-only, time-orientated, ordered sequences. So really, really dry bit here. Time, for the context of this particular definition, is a very loose concept. Time simply means that things are relativistic, so that given time n plus 1 is after n. So time is not necessarily wall clock time, although it can be if you want to lock yourself into reality or not. But it doesn't have to be, as long as it's got causal dependency. So a sequence, an append-only sequence of which is time ordered. So a little bit of audience participation to start with. So has anybody here considered using a log as a data structure before? 1, 2, 3, 4. 4 people, awesome. And then out of you guys, I suspect, has anybody used log data structures, or the data structure, the log, to solve any real-world problems? Like every day you're sat at your desk, you're trying to solve a real problem. Anybody? One person, amazing. Okay, so one person in the room has used logs to solve a real technical challenge. So the first thing to kind of dig into with this is that this is nothing new. So nothing I'm going to talk about today should blow anyone's mind. The log has been around since the dawn of time, pretty much. If you think back to banks, for instance, we just had a really interesting talk over there about banks. Banks use logs all the time to audit. So every single transaction event inside a system is logged, and they use that for an auditing capability. It's also been around as a data structure since computing. It's one of those data structures that nobody really talks about because they actually think it's far too simple, it's far too easy. What is a log? Who cares? It's just like a list, yes, but it's not really a list. It's not really an array. It's an entirely separate data structure that nobody really talks about. And it's this, really. It's as simple as that. So you start off with record 0, and you add another one, and it's at record 1, 2, 3, 4, all the way up to 12 in this particular instance. And you just keep appending and appending and appending. So the real question is, given that we have a room full of technologists, we're talking about a data structure that's been in existence since the start of computing. Why have I only got one person who put their hand up for 2 things? I mean, that's crazy. Yeah? If I asked everybody to put their hand up for people who had used a list to develop real systems, how many hands would go up? Yeah, good. An array? Yeah, brilliant. So we have this fundamental data structure that nobody seems to use. It's just kind of dropped off the kind of sphere of knowledge. And I personally believe, and this is me self-quoting, how classy is that? I believe that logs are an underutilized by the vast majority of web engineers. I wish I put a strike through the web there, because it doesn't really matter. And I was trying to get at the idea of non-deep system engineers, because deep system engineers actually probably know what I'm about to talk about. But if I use web as a kind of loose expression around people who build products, who build things that people interact with nowadays, especially given that the theoretical domain of logs, which hopefully I'll dig into a little bit, but without scaring anybody, offers really, really, really powerful use cases. So like any core data structure, you have people like Dijkstra talking about logs back in the day, when systems were just being built out. If you all the way back to kind of von Neumann, when he was building his machines, logs were things that they talked about in those early papers. These are fundamental things. So I believe that they're really underutilized. And so, right at the start of this talk, I asked for those questions, and I got one response. But actually, if we kind of look back at it again, who has used log-based data structures to solve real technical problems? Well, actually, you probably have. Yeah. So whether you know about it or you don't know about it, you almost certainly every single day of your working career use logs, because virtually everything important is based on them. So every data store you have ever used, pretty much, is based on a log as a core concept. So whether that's the write-ahead log in something like Postgre, log shipping, if you've used SQL Server to move data from one place to another. If you use CouchDB, and some of the guys behind CouchDB are in the other room, they have this concept called changes, which is like a feed of every single event and every change that happens. They're all just logs. And then the second side of things is distributed systems. So again, we've had a couple of talks today in here around, is it Kubernetes? I can never pronounce it. Mathos, let's use that one. Around clustering systems and around Docker and all those things. These are all really important changes for us as a profession, but absolutely behind all of those things is this stuff. So things like multi-paxos and Raft and Zookeeper. I suspect everyone's heard the word Zookeeper a couple of times today already, because it's like the one that everyone picks up. Basically, they are distributed versions of logs. That's all we're talking about, is the idea of a sequence of events which happen in order. That's it. So have you used any of those recently? I mean, I can't imagine my day job if I didn't use at least some of these things. They are fundamental to everyday life for me. So what makes them interesting? So I've kind of given a kind of vague view of what a log is. So why do I think that they are really, really interesting? And actually, it comes down to a few different things. The first thing is that they're really, really powerful. And what does powerful mean? So at the fundamental level, what a log provides is serialization. So I don't know if you can kind of hark your head back to those times when you were at university and you were talking about how to build systems. And serialization was like 101 when you were talking about databases. Everyone was talking about ACID, and ACID is all about serialization. If you can define the order of something in a deterministic system, then you can, by definition, provide fault tolerance. And one of the things that we all do, or most of us do every day, is build systems that if they go down, people lose money, people lose jobs, things go terribly. People can potentially lose lives. By building a system that is serializable and deterministic by default, you get these two incredible facilities. So the first is recoverability, and the second is availability. So why is recoverability important? So we all know from reading the internet, and certainly some of the Erlang guys, embrace failure. Yeah, hardware breaks, systems go down, things break, deal with it. Now, one of the ways to cope with that is to engineer a huge system that handles every eventuality. Good luck with that. But one of the things that falls out of systems that are architected around a log is this concept of recoverability. So if a node goes down, actually all it really needs to do is replay all the events that came into it. It's deterministic. If the system is deterministic and behaves rationally based on input, if you store down all of the input to start with, To recover a system, all you actually need to do is replay that system. Because it's a time-ordered sequence, you have all of the guarantees that you need to replay a sequence at a future point and rebuild the state of that system, whatever that system may be. And the second is availability. And this is actually exactly the same problem. So if you imagine the problem is bootstrapping a new node. Node dies, we need to rebuild that node so that we can continue serving. Well, availability is solved purely by just doing that ahead of time. If you have a node and you want to make sure that it is available should that node go away, all you really need to do is replay all those events to the second node or the nth node. If you have n different nodes, the probability of all of them going down reduces, and therefore you are in a position where you are more likely to be available. Now, to get to 100% availability, you can go into the statistics. 5 nodes is fine, generally. But if you have 5 instances of your system, and each one of those instances is just following the same log, then you will always guaranteed, or no, you're largely guaranteed to be available, and if any one single node goes down, you are recoverable. So, what does it look like? It looks like that, really. So you can imagine, this is actually how a lot of databases work behind the scenes. In fact, let's just say that it's SQL Server. So requests come in, they modify a master. That master makes changes to a log. In SQL Server, there's a couple of different logs, but there's a write-ahead log, so let's talk about that. So before it makes any changes to its internal state, it writes down, this is the thing that I've been told to do. It then internally mutates that state. And actually what it sends to all the slaves is simply the log, the same command that it received. At which point, because those slaves have historically witnessed all previous states, their new state is merely the delta between the two, and therefore it can be replayed, and that makes it really, really powerful. Yeah, it actually means, and although this isn't true for SQL service, it means that you could have an arbitrary number of these slaves, yeah, because actually they're just reading the log. So the second thing is that they're super flexible. And this is actually my favorite thing about log architectures. I think it's really, really cool, which probably says more about me than anything. So because the state of a deterministic system, which is based on a log, can be represented by the log and a single number, it means that not only can you recover and you can make available, but you can also replay to any individual point. So let's say, for instance, you've got a database, and the database in a traditional web system will record things like state. So customer X, let's try and work this out. So customer X is currently an active user. There you go, there's an active flag. Or no, actually, let's use the brilliant example from the previous talk about banks. So there's a credit card, and the credit card is currently usable. So there's a Boolean flag that says, this card can be used. Now, if at some point in the future that Boolean flag is changed to this can no longer be used, because of the loss of information there, you can never ever question, okay, when did it lose that ability, or what was its state at time X? Now, obviously, you could architect your database in an entirely different way. You could store the date time, for instance, for when it was activated or deactivated. So you have one instance of when that state was like that. But if you try to do that for every single Boolean and every single instance, let's say I changed my name, do you store down all of the previous states of my name? Do I store down all the previous states of my liquidity as a human being, all the previous states of my balance? You can imagine how this database suddenly gets really, really complicated. And that's because it's storing current state. Now, the big advantage with a log system is all you do is you append to that log. You just say, and now change the state to this, and now change the state to this, and now change the state to this. And what that means is by starting at the start of the log and following all the way along to a point in time that you care about, you can recreate the state of that system at that time. And so if you imagine, for that particular case, my bank balance, God, don't talk about it too much, you can see that I spend some money, I earn some money, I spend some money, I earn some money, I spend some money, I lose my job, and then and it's all terrible. But you can imagine what value had Roger got at this point. All I do is replay to that point. And if you can imagine, if you snapshot along the lines, along the time, so what I effectively do is materialize the state of the system at various points. It means I can replay that really, really quickly. So what's super powerful is I can ask questions like, at 11 a.m. yesterday, how many of my users in my system had ordered a t-shirt? Now, right now, it might be 300. At 10 a.m. yesterday, it could be 1. Normally, that's really, really complicated to identify within a traditional system. And so, and then the next thing is that it's distributed. So the beauty of a log in general is because it's append only, and because it's sequentially ordered, it makes the concept of distribution very much easier, because effectively all you need to do is say next, next. So whenever I read something, whenever a new event is added to my log, all I need to do is make sure that I propagate out that log change. Now if you associate it with a consensus protocol, and I don't know how many guys in here know about consensus, things like Paxos, things like Raft, what they effectively do is ensure that given a set of computers, a set of machines, a set of instances, they all contain, at this one moment, the same view on the log. That's effectively what they do. They do it in lots of clever and interesting ways, but ultimately they say, given a log, and given an ID, which is the point in time on the log, all these computers can agree that they are currently representing number 5. And then when they add an extra one, they say next, 6. And so what that allows you to do is build distributed systems almost trivially, because effectively at the center you have a set of logs, or a log, and then a set of separate systems that are stateful but effectively stateless between themselves, which can all represent the current truth. Now with Paxos and things you can be consistent. If you remove Paxos, what you effectively have there is an eventually consistent system. Really, really simple. And then again, this is kind of what it looks like. So you can imagine you have a system that writes to the log. So that could be, let's say that you are building an e-commerce system, and what you do is, this is the orders log. And what you want to do is every time somebody tries to make an order, you record that in the log, and then you distribute that change out to all those peers. And then so long as all those peers agree using consensus, or that when you read you are happy that they can be inconsistent, you can have as many of these peers and they should all represent the truth, because they're all built off the same log. So all that's like super nice. It's kind of really interesting that this really old data structure can have such varied uses. But kind of what does all that mean? So I've said a load of things. I've said that they can do powerful things and distributed things, but like what's the relevant use of any of these things? So let's give ourselves some challenges. So let's talk about integration. Now, I don't know about you, but I've done quite a lot of integration in the past. When companies say we want to use X or Y, and you have to go Y, and you have to try and kind of cajole your system into providing the information. So what I would say is, in most organizations, the vast amount of information that those organizations hold is entirely untapped. If you've ever been part of a BI rollout, where you try and add business intelligence to an organization, you'll understand that most of the information that is valuable to that organization is entirely indiscoverable. You can't find anything about that organization around, for instance, the number of sales during a peak time on a Wednesday. That's really, really hard for a manager or a senior manager to ever get visibility of. So BI is there to try and provide that. In order to do so, you have to kind of intricately lace the business intelligence systems into the current system. And that's typically done with things like ETL. And ETL systems that I've been exposed to, at least, are typically reasonably slow. They're super expensive if you get a company like Detica or somebody involved, and they tend to be quite unreliable. So I don't know about everybody in the audience, but I've worked on systems which are batch orientated, so you get to learn about yesterday's events tomorrow, which is super useful if you're a real-time modern business trying to do kind of on-demand ordering. And they tend to be things like Windows services running on a blessed box that when it goes down, everybody has a panic attack and has to get up at 4 a.m. in the morning. So This is what they tend to look like, obviously in a code way, although that probably is an integration project, let's be honest. And so what I'd say is like challenge accepted, yeah? I mean, this is something we can solve with logs. So how can we do that? So the beauty of a log-oriented architecture is it decouples all the readers from each other, and it decouples the readers from the writers. And effectively what it provides is, as a system, you publish events. You say, this thing has happened. I changed Roger's bank balance from £1 to £2. Or actually, I added £1 to Roger's bank balance. Because the system is publishing those events to a log, and that log has order and therefore is serializable, it means that not only can the thing that I originally intended read that log, so for instance, in this instance, let's think that it was a database that allowed me to see my current balance, that materialized that state, that chain of state changes into a single thing. So is that me? No. Okay. But what it also allows is any other system to read that same log. If you imagine that log has 1 billion entries and has gone back 2 years, and BI comes in and they say, Roger, we really, really, really want to be able to do business intelligence over every single bank balance change across our entire system. Now, if I built that thing traditionally, I'd go, I can't do that. I haven't got all that data. With a log-based system, yeah, okay, start at the end of the log, and at the beginning of the log, sorry, and read forward, and materialize that into whatever version that you want. And the beauty is that it's not blocking. So while that person or that system is reading that log, it doesn't stop any other system reading that log. It has no effect on any other reader. And therefore, what it provides is the ability for multiple systems to read the same data at the same time without ever creating any form of back pressure, where back pressure can be a horrendous thing in systems where one thing is waiting for another and then it stops this, and it's sort of terrible. So this is kind of what it looks like. So you have a data source that's kind of writing onto the front of the log. This is a change. This is it changing my bank balance to 12. Yeah. And then you've got system A, which is all the way back here, and it thinks time is 7 in this particular instance. That's its view of the world. The beauty is it knows its view of the world. It knows it's 7. So if you ask it what state are you, it can say, oh, I'm 7. It doesn't get confused. You don't have to say, are you all consistent? You can simply say, you don't have to anticipate them all being consistent. You can simply say, are you consistent, given the fact that I think, as a reader, I'm number 12. It says, well, no, because I'm 7. Eventually it will get to 12. And then you've got system B, which is ahead. So it has a different view. It has gone on from the system A's vantage point. But because they are entirely separate and they are not in any way coupled, it means that they can both have a valid view of the world. And then from a kind of how do my team build these things kind of point of view, this is the way that I like to kind of perceive it. So you have a set of source systems. So each one's got a publisher. So this one can be the website and this one can be the mobile app. And each one is publishing to this log system. The beauty is that these guys don't have to care about these guys at all. So as a consumer, I can add another one of these teams. Yeah, I can add my BI team, Consumer Sigma, and Consumer Sigma can have as much access to this log as Z, Y, and X, which is really, really powerful. Yeah, it's totally decoupled from a technical point of view, but also from a team point of view. You want a new functionality? Spin a new team up. Get some awesome devs in a room. There's the log. There's the data source. Materialize that into the way that you need that data. So the second one is the view challenge. So typically, I always prefix everything with the word typically because it's not always true, but typically within a traditional database, data is stored relative to the view that you care about. So the view that I'm going to put live, the view that I'm going to show to the humans, or the view that I kind of regulatorily need to keep of that data. But what it isn't stored as is necessarily all of the ways that you want to use it. So again, back to that kind of BI problem, or let's say search, for instance. So in search, the way that I would store data would be fundamentally different than the way that I would store data for, I don't know, auditing reasons or for financial reasons. So let's have a think about that. So what does that really mean? It means that if I have data in a particular format and I want it in a different format, what I have to do is, one, hope that I have stored enough state and enough knowledge around that state to recreate the form that I want. And then secondly, I then have to create some form of ETL process which converts that thing through a set of modifications to the format that I care about. And the beautiful example of this is Lucene. Yeah. So if let's use Elasticsearch. So Elasticsearch have solved this problem, or tried to solve this problem. So what they have inside Elasticsearch is these things called rivers, which is actually a bit like a log. And what they do is they scour your database for changes, which doesn't always work because of the way that databases are built, and then they transform that thing. So let's say challenge accepted. And so what's the solution for the log? So the beauty of this is that, let's say we have one log, for instance, and mostly I've talked about so far is the idea of one log. It means that you can restart that log with an entirely different system which views that data in an entirely different way from the start. But then if we expand that to the idea of multiple logs, so for instance, maybe I have a log of orders, but maybe I also have a log of new users, and maybe I have a third log of basket items, things that people have put in the baskets. So traditionally, there would be three tables. These are the things. This is the state that they currently are. But what I've got is all these changes. And I can re-mold those. I can re-entangle those in any way that I want. So I can answer questions like, how many of my users, after adding an item to the basket, went on to order? Or how many orders were predisposed by a user joining and then adding particular item of basket A to my system? Because those are fundamentally separate things, are immutably set in in time, I can replay them in any way that I want, and that's really, really powerful. And so it makes secondary views really tractable. So let's use the Lucene example. All I would basically do is set my Lucene to read through all my previous log and recreate the data how it needs it, tuples and all those good things. And this one particularly is really interesting to me. So automatic cache invalidation. So I don't know if you guys all know the quote that there are two hard things in computer science. One is naming variables, and the second is cache invalidation. But going back to a point I made previously about systems knowing what state they're in, they by definition have cache invalidation built in. Because if a system knows that it is currently at version 7, and I tell it, tell me what you know, oh, and by the way, I think the system is in number 12, it by definition knows that it needs to catch up in order to answer my question. And that's really, really powerful. What it allows you to do is build systems which are extraordinarily quick because they know, or they know the format and they know the version of data or the state of data that they need to represent in order to answer my query. And that means that they can do all kinds of clever things behind the scenes. So this is the kind of thing that I'm looking at. So you can imagine you've got this log, and let's say at first we start putting data into this, and then we make use of a key value store to store latest versions of information. That follows the log. As the log changes, we modify the internals of that. And then one day your boss comes over and says, hey, Roger, it'd be awesome if we could do free text search on this. So all I do is I spin up a new thing that reads from the same log, starts from the bottom. And then, we need monitoring and graphing, because nobody knows what's going on. Does this thing go down? Does this thing go up? So we add monitoring and graphing just by reading that same log. And then we want to store it forever, so we shove it on a Hadoop cluster and we do big data crunching on it. So basically what it allows you to do is decouple everything and build multiple views all over the place. So a couple of examples. So what if we want to display the order rate on the website all of a sudden? We don't have that information. We could try and calculate it. It could be really hard. Maybe we don't store timestamps in the database. So all we do is we just listen to the order system. Personalization, one of my favorite subjects. we want to suddenly try and personalize the website in order to boost profitability. Big evil corp number X. All we do is we read the financial log, and we apply boosting whenever a particular event occurs which increases the finances. So we can start kind of combining multiple logs. So order X correlates to finance log X, and therefore we can say, okay, well, this seems to generate the most value for us, and we can push forward with that. We can build metrics around individual merchants. We can do full text search around all purchases. All these things become kind of reasonably trivial because it's just another system reading the same log. I feel like I'm repeating myself, sorry. And then the last piece that I'll kind of touch on is scaling. So I've been really lucky to work on some systems that have gone from reasonably small to reasonably massive, and have handled millions of customers and billions of pounds. And part of the thing that you realize is when you start out with your little organically built application that suddenly becomes successful is that, God, you wish you had some kind of scalability handle that you could turn. Because most of the time, no matter how well you've built it, you cannot anticipate the amount of weird behavior that a distributed system provides. And so it does that by removing dependencies between systems. So some of us have probably worked on this particular system. So you can see that like everything is just talking to everything else, and it becomes an order n problem. So you've got new Hadoop thing which talks to your Teradata, and your Teradata talks to your RabbitMQ, and God only knows what else happens. And over time that becomes incredibly complicated. I've sat in rooms where people have kind of had discussions around particular components and whether they could remove them or not knowing what dependencies they have on other systems, and then those dependencies have on other systems. You turn one thing off, or you turn one box off, and the entire system falls to bits. These are horrifying things as an engineer. But with a log, what we can definitely do is remove that kind of order n kind of combinatorial increase in connections between instances or systems, and replace them with a centralized place, a single point of truth, but a single point of truth which is trivially scalable in and of itself, because a log is just a append-only list. We've been doing append-only for a long time. You can do it extraordinarily quickly, but also because each independent log, each independent set of events can work in a different way. You can have multiple logs, which is super powerful. All scaling does is require adding more consumers or materializers. So let's say we look at the key value store from the previous example. That was storing the current state so that it was quick to access, and it was updating as soon as it realized that it needed to change. Let's say that we suddenly get 1 billion hits. Let's say that we're Twitter. All you need to do is add a second one that's doing the same thing, or a third, or an nth. The same goes with every single component in the system. If you have suddenly a huge amount of additional BI requirement, well, why not just spin up a second or a third or a fifth instance of the system which provides information about the log? So scalability just becomes a process of adding instances. And basically the whole system can be considered, the system that you build, an eventually consistent database. Yeah. So if we kind of boil everything down, all the systems that we create are abstractions over what a database really is, which is a method to input and return data. That's what we do. That's what systems are. They transform, they modify, they materialize, but they effectively just change state. And so by allowing us to boil it down to a single concept of this is a database, it might be a fairly unusual database, but it's a database at the heart of it. What that allows us to do is reason about the system as if it were a database. And it's interesting that databases have solved this exact same problem using this exact same method. And that's kind of the way it ends up looking. Yeah? I mean, so you have all these domains, all these functionalities here that may well talk to each other, certainly if they're external SaaS vendors. But what you have here is, a unified log which has the truth, and all these things can read from it. And that's, really, really nice. So ultimately, to wrap up, why logs? So by sequencing events, they ensure consistency of data and understanding across an entire system. They allow scalability through really simple means. Just add another instance of the thing that you care about. They decouple consumers So they trivialize integration. All you need to do, add a new thing that you care about. They facilitate new views. So if you care about something which looks different than a previous state, because you have all of the state all of the time, you can always recreate and you can always modify and take a new view. And availability is simply a matter of adding another instance. So if you're scared that one of your instances is going to go down and it's super important that it doesn't, all you do is add another one. You've got less likelihood of it going down as an overall system. So a bit of audience participation again. Who thinks they will take a look at building systems on logs after this talk? We got, oh, that's nice. I like that. Okay, cool. So given that, I have two things. First, this book, Unified Log Processing, it's in early release. It's not written by me, I wish it was, but it's really, really good, and you can get early access to it. And then the second thing is go here. So this entire talk actually is based off a paper/white paper that was given by LinkedIn a few years ago, around about 2012, and it's based on the idea that LinkedIn was struggling to scale and struggling to solve all the problems that LinkedIn had, obviously massive integrations and the rest of it, and what they did is this. So they took their entire system and they rethought it, and they built things like Kafka. And Kafka is actually a system which is built around the premise of what I just talked about, and their entire infrastructure now is based on the concept of lists, logs, Jesus, and wow, that was bad, isn't it? So their entire system is based on the concept of logs, from everything from chat through to whether you want to be employed or whatever. And that paper is really, really good. It goes into a huge amount more detail than I have and explains everything better than I did. So, thank you, and thoughts, questions, or otherwise?
Quick one. If you've got 10 years worth of logs to replay up to last week,
yep.
Wouldn't that take a long time to replay all of that?
Depends what it is you're doing. So 10 years of logs could be 3 entries, yeah? Or it could be a trillion. So again, the problem is as scalable as the problem space, yeah? So if you have, let's take a ridiculous example. We're talking about CERN, yeah? So CERN generates like 7 terabytes of data a second or something crazy, and it does so in a log, hilariously. So what you effectively do is, if you get involved with CERN, you're a big physicist and you want to care about what they're doing. Basically, what happens is you get this huge data feed, this fire hose, as Twitter would call it, which will break any computer you've ever seen. But if you care enough about it, you build a system that can cope with it at that speed. Now, there are advantages in, if you believe that you can represent the state in a format that you can do that snapshotting piece, yeah? So, for instance, for the recoverability, what I would say is, so let's use Lucene as an example. So my Lucene reads in all of my ad product to my system. So I've got an e-commerce system, and every time I add a new product, it creates an add product entry in my log, and every time I delete a product, it removes it. So I build a system that reads through the log, adds those instances, those entries into Lucene when they're added, and removes them when they're removed. And obviously, because that data is well defined, I understand what part of that log or that data I care about. I could, in theory, snapshot that data. So I can say, at the start of each day, build a snapshot of the state that is currently in Lucene, use that as the base, and then modify, run your deltas on that. So it's exactly the same as Docker images are a perfect example. No, Git. So it's how Git works, yeah. So Git, again, is just a log. All Git is a log of deltas, of changes of code. So it's exactly the same system there. So if you snapshot at any point, you can always replay. Hi.
What do you think of Bitcoin's blockchain technology as an example of what you're talking about?
What do I think about Bitcoin's blockchain technology? So I have a story about Bitcoin. I lost a lot of money. Yeah, I know. So I joined the whole Bitcoin thing kind of fairly early on when it was like 4 cents for a Bitcoin. So I bought like 100, I think, and then I sold them when they were 90p. And it was like, yeah, amazing. And like a month later, they were like £1,000. I was like, what? I'm an idiot. But no, what do I think? So it's really, really interesting, because it's actually fundamentally it's telling the same story I just have. Because actually, what what Bitcoin and the blockchain is all about is providing a consistent, reproducible chain of events, a log of these transactions have occurred, and by doing so, and it obviously it uses a consensus protocol, it's none of those, but it's its own internal consensus protocol. But by applying a consensus protocol to a log, what you actually have is the monetary system that is Bitcoin, which is extraordinarily powerful. And it's also powerful for other things, that you can use it for storing digital signatures and all kinds of cool things. So, you know, what one of the nice things about that example is that it's actually fundamentally solved something called the Byzantine generals problem, which is basically if you have a set of systems which are cooperating on what a list currently looks like, so what state that list currently is, but one of those instances lies, i.e. it's a baddie, it is possible using some consensus protocols to modify the log in the past. So that's effectively what it does. It's, you know, this event, this event, this event, this event. What the Byzantine generals problem states is that you could, in theory, change a previous event and then tell everybody else that that happened. And so what the blockchain does is, by using a log plus a consensus protocol, is solve that. And it solves it in a way that has, you know, as far as I'm aware, not really ever been solved properly before. So I don't know, what was the question? Do I like it? Yeah, I think it's awesome. Yeah. Any more questions?
This is a vague question, so I haven't thought it through. But if you've got data that is sensitive, like some of the Data Protection Act, and then you log every transaction, you're storing that data possibly for longer than it was needed for the original purposes of the
Yeah, that's interesting, isn't it? So by record, so all a log does is records this event occurred at this point, and this event occurred after that event. Is effectively what it does. And the data protection asks you're only allowed to store particular data for a certain length of time. Yeah. So snapshotting would get around that. So as long as you have the authority to continue, so you're I'm trying to remember my data processing, so you're a processor in this instance, aren't you? So the Data Protection Act would call this system a processor, therefore you have the requirement to look after the user's data for the 7 years, I think it's 7 years. So you could snapshot up to the point where you only continue having 7 years of the new event, so that would be useful, or you can garbage collect. So for instance, if a user is still current, you can keep their data perpetually, yeah? So long as you tell them that you have their data and that data is relevant to your uses, then it's perpetual. If the user then leaves, then they have the right to be forgotten. I think that's the general gist of it. So what you could definitely do is have a garbage collecting system in that instance. So if you imagine you have the log, it would be very easy to have a process that went through that log and gave a different view of that log, which is the view without all the users that are no longer here after 7 years. So you can use the system to solve those problems. I guess that by default it doesn't solve that problem in particular, but I don't think it precludes solving it.
Kafka appears to be dominant
Yep.
space, perhaps rightly so. Is there any alternative coming out?
Yeah, so Kinesis, which is AWS's hosted version of Kafka, does. I mean, it's really complex. So it's just you could build something like this. It's just a text file that you append to. So from a point of view of are there alternatives? There are huge numbers of alternatives. It depends on what your use case is. So Kafka is brilliant because what it allows you to do is set up an instance that allows you to replay through logs really quickly, that has things like redundancy and availability built in by default, which allows you to base an entire system on top of it. And the same goes for Kinesis. Kinesis goes one step further by removing management from that too. But there's nothing stopping anybody in this room writing kind of a log. I suppose it depends on the use case. But those are the only two that it's Cloud Wars. I imagine that Microsoft will have one out next week, and Google the week after. But I mean, big companies like Google have these kind of things already as part of their organizational structure anyway, which is why they have that thing called Cubby. Cubby? Is it Cubby? Chubby, there you go, which is their kind of implementation of Zookeeper, and they use the log versus that. And obviously their log is all the input data. But yeah, at least that's what my understanding of Google. I've not worked for Google. Okay.
And when you've got logs and time,
Yep.
and so take for example banking.
Yep.
So you've got transactions running, and then you're paying, and you get your snapshots, and it's all great. But then someone's realised they were supposed to change an interest rate a week ago. How is things like that get managed with a daily log? Do you just kind of how do you adjust it or say back to the source? Everything depends on the time, but also that should happen.
So if you imagine, it depends what you call your truth, yeah? So if you imagine you have a sets of events, you can always replay those events into effectively like a branch. You can imagine like there's a branching system. So let's say, let's use your example. Sorry, the question was for the camera, how do you modify historic data, pretty much? And so the way to do that is, let's say all the readers are currently reading off log, and we call that log. If we wanted to modify the data from point N in log, what we could do is we could create a new system that reads the log, it reads that log, and then at point N, it starts creating a new log, and then you just redirect all your readers to that new log. So that's just like a modified version of that initial thing. So it's like branching and forking in code, yeah? I mean, well, it's not just like that, it's literally that. So all a branch in Git is effectively what you just said. You know, given this event, branch off, make your changes, and then eventually, in theory, you could merge them back in again. Yeah. Does that kind of answer the question? Cool.
Or you could also add new logs.
Yeah, of course. Yeah. So as you care about new things, you can add new logs, and you can then incorporate them. The beauty of the whole thing is that you can just say, okay, so this is what our data system looks like right now. This is what the state looks like right now. But we've just added this new log. Wouldn't it be brilliant if we could incorporate that into all of our previous data? At which point you just start a set of new nodes, all running from the start of the log, run through everything, and there you go. There's your brand new set of data, and you just switch over. You know, that's the current status of the system. That's the current status of the other system. I'm just being told that there's 1 minute. Anyone got any burning question about logs? No? Not surprising. If anybody wants to join me for a beer later, I'll talk about logs until you go home. Fun guy. Okay, brilliant. Thanks, everyone. Cheers.